Hello. You have probably already observed my videos on rational functions and their graphs. And the links that I posted for some of that came from my college algebra class, where they were responsible for vertical and horizontal asymptotes, but not oblique. But in this pre-calculus class, you are responsible for oblique asymptotes. So I want to go ahead and talk about how to find those and like what it looks like when you graph something that has oblique asymptotes. These are asymptotes kind of like in the sense of a horizontal asymptote, but it's oblique, which means it's slanted. So it's not horizontal, it's not vertical. But it gives a nice idea of the pattern or progression of the graph along that invisible line, that invisible slanted line. It's still a line, but not vertical or horizontal. And it's pretty easy to recognize when you're going to have one. Just like in the video that talked about the horizontal asymptotes and looking at your degrees of your numerator and denominator, you're going to do the same thing for an oblique asymptote. So again, this is for rational functions. So, we're dealing with the functions that are fractions with x either in the denominator or both numerator and denominator. And these occur when the degree of the numerator is exactly one more than the degree of the denominator. Okay. Found. How do you find it? Found by dividing the numerator by the denominator and ignoring the remainder. So the equation of the line will be y equals the quotient. Put that quotient without the remainder. And that'll be the equation of that invisible asymptote. So you can have more than one vertical asymptote. And then in addition to that, you can have either a horizontal asymptote or an oblique asymptote, or you could have neither one of those. That could happen too. But you could have a horizontal or an oblique, or neither of those two. All right, so I guess I should write that down. The graph may have more than one vertical asymptote or none. So that's a possibility. And the graph cannot intersect a vertical asymptote. And then there can be, at most, one other non-vertical asymptote. So that's where we're talking about horizontal or oblique. So it can have at most one of those in addition to possibly vertical asymptotes. So most one other non-vertical asymptote, and the graph may intersect that asymptote. May or may not. It just depends on the situation. Often these asymptotes, if it does intersect, it still kind of shows you a pattern for how the graph's heading. All right, so let me try to sketch you a little example of the situation here. Let's say you have a function f of x equals x squared plus x over x minus 1. And your job is to try to graph this. Now you might want to go ahead and do any factoring to see if any reducing can happen, because you always want to rule out whether it's a graph with a hole. But in this case it's not. It's factors into x times x plus 1 in the numerator, x minus 1 in the denominator. Doesn't reduce, so we're not going to need to be worried about holes. But do notice that in the original function, before I factored, the degree of the numerator was 2. Degree of the denominator is 1. Remember, the degree is, when you have the terms written in descending order, the degree is the exponent on the first term, that highest exponent. And since the degree of the numerator is exactly 1 more than the degree of the denominator, then we know we're dealing with an oblique. All right, and then to find that oblique asymptote, you would divide x squared plus x, which I'm going to go ahead and put a plus 0, by x minus 1. And since you're dividing by x minus 1 in this case, you could do a synthetic division situation. I'm just going to go ahead and do long division, just because I have it already written here, kind of. All right, we don't care about the remainder. We just ignore that. But that quotient tells us the equation for that oblique asymptote. And that is going to be y equals x plus 2. So we're going to graph the line y equals x plus 2. We're going to use a nice dotted line. And that'll help us in this situation. All right, you know what? I'm going to move to the next slide just because, well, I might go ahead and, I don't know. I was debating writing over the graph paper, but I got plenty of space. So let's go ahead and go to the next slide. So my oblique is y equals x over 2, y equals x plus 2, excuse me. And the original function, again, was, shoot. Every time I tap this, everything erases. All right, my original function was x squared plus x over x minus 1. So I can also look for my vertical asymptote by setting the denominator equal to 0. So I find out my vertical asymptote is x equals 1. I can find my intercepts, my x-intercepts and my y-intercepts, and that'll help me a bit. So remember, with x-intercepts, you plug in 0 for y. Well, in order for a fraction to equal 0, just need to worry about the top equaling 0. So you've got 0 and negative 1 for your x-intercepts. Then for the y-intercepts, you plug in 0 for x. Oops. and you end up with 0. So it intercepts the origin. All right, so far in our graph, how is this looking? I'll do my best to draw this graph and not be too shaky. All right, so every little tick mark is going to be worth 1. All right, so vertical asymptote x equals 1. So then we know we're going to do a nice dashed line at x equals 1 for the vertical asymptote. For the oblique asymptote, y equals x plus 2. So that has a y-intercept at 2 and has a slope of 1. Up 1 over 1, up 1 over 1, or down 1 over 1, down 1 over 1. So it's going to look like this. And then x-intercepts at 0 and -1. And y-intercept at 0, 0, 0, origin. That's that intercept there. And after that, we can just do basically an xy table to come up with some more points to get a really good idea about how this graph's going to look. So that's where we head from here. Nice little xy table. Let's see. So, like if I were to, let's see, what would be some good values to plug in? Like let's say I plugged in -2. If I did that, I get 4 minus 2 is 2, so -2/3. So roughly here. And then if I plugged in 1/2, 1/4 plus 1/2, 3/4 over -1/2. So -3/2. Let's see, let me double check that again. I'd have 1/4 plus 1/2 over 1/2 minus 1. So 3/4 over -1/2, so times -2 over 1. This would be 1, 2, so -3/2. Yeah, so 1/2 comma -1.5 basically. So over here. So that gives us a rough idea of how that piece looks. Maybe I should do a different color so you can kind of see it better. But then we still need to see the piece that's in, like, you see how the two asymptotes intersect to make an X. There's going to be a piece opposite on that X, in that X. So let's do a couple more values here just to get a rough idea about that other piece. Let's say that we plug in 1.5, and then we plug in 2 and 3, just to see what it looks like. All right, so if you plug in 3, you got 9, plus 3, you got 12 over 2, which is 6. So 3 comma 6, 1, 2, 3, 4, 9. Perfect, I drew it up to 6. If you plug in 2, 4, you're going to have 6 over 1, so 6. And then if you, that's just not looking right. 2 times 2 is 4, 4 plus 2 is 6, over 2 minus 1 is 1. Yeah. Okay. was looking at my graph on Desmos and it doesn't quite look the same. But yeah, okay. Yeah, it's got 2,62. It just looks weird on the graph. Sorry. Getting a little distracted there trying to look at it. Okay, and then if you look at the 1.5, let's see here. That's where I'm going to use the calculator and just put it in. So I'm going to put it as 1.5. I'm going to do 1.5 squared plus 1.5. That's 3.75 over 1.5 minus 1, which is 0.5. So divide by 0.5 and you get 7.5. That still doesn't make sense either. Sorry, let me do this again. 1.5 squared is 2.25 plus 1.5 is 3.75. Okay, and then 1.5 minus 1 is 0.5. 3.75 divided by 0.5 is 7.5. All right, 1.5. And then so we're looking at 2, 4, 6, 1.5. I'm not sure quite what's going on in my head here, but I do know that the pattern looks basically like this for that piece. Oh, okay. I see what's happening on that one. Again, I'm trying to look at the Desmos, so I'm just going to kind of cheat and trace over it right now and see what the ordered pairs are. And I am correct that it's 7.5. It's just in my head it was looking a little weird. So I think it has to do with my sketching on this grid here. But those are correct values. And that'll give you the little curve, that blue curve up there. You could do more if you want to get a little more refined. You could do less if you wanted to. I mean, you really couldn't do less. I'm sorry. Like, that would not really help with the shape. I would say, if anything, err on the side of doing too much. So I would do more. But anyhow, all of that said to demonstrate what's happening when you see an oblique asymptote. So you can have one of these possibly if, like, when everything's as simplified as possible and you don't have holes, then you're looking at having a degree that's exactly one more in the numerator than the denominator. And this can occur. Okay. And another thing that didn't really get covered in the college algebra video, and I'm not even going to go too far into depth with this here. If you take calculus, you'll get into this more. But if you look at formal definitions with f of x, I'll go back to black here, with f of x equal, being your rational function, equal to p of x over q of x in lowest terms, and a and b are real numbers, P and Q are polynomial functions. All of these parts laid out. So you have, polynomial function where it's a polynomial over a polynomial, or a rational function, sorry, where it's a polynomial over a polynomial. Then consider it written in lowest terms, real numbers A and B. There's two formal ways of writing about your vertical and horizontal asymptotes. If the absolute value of f of x goes to infinity as x goes to a, then x equals a, then the line x equals a is a vertical asymptote. If f of x goes to b as absolute value of x goes to infinity, then the line y equals b is a horizontal asymptote. All right, let's look at the situation where we have f of x equals 4x minus 2 over x plus 1. All right, for this situation, we know that we need to, we could go ahead and do a little reduce or a little factoring just to make sure we don't, make sure it's in lowest terms, which it is, because 2x minus 1 and x plus 1 are two different factors. That's not going to reduce. So it's in lowest terms. And the 4x minus 2 and the x plus 1 are both polynomial functions when they stand alone, and then put one on top of the other, make this rational function f of x. And then if we want to go ahead and graph it, we already, from our experience, know that we would set x plus 1 equal to 0 and get x equals negative 1 on the denominator in order to see what that vertical asymptote would be. And then we also know that we can look at those degrees of the numerator and denominator, and we see that numerator has degree 1, denominator has degree 1. So then the horizontal asymptote is y equals the ratio of the leading coefficients. So 4 over 1, which is 4. So y equals 4 would be the horizontal asymptote. And that's it for our asymptotes. Because we know from that, like, we found all the vertical ones possible, so in this case there's only one. And we know that since we found a horizontal asymptote, there's no other horizontal asymptote, and there's no oblique. Which, I mean, we know there's no oblique because of the whole situation with our degrees in the top and bottom being the same. If the degree on top was exactly one more than the degree on the bottom, then you would be dealing with your oblique and not a horizontal. But that's not what's happening here. So let's see here. How's this graph supposed to look? You could go ahead and try to look for your places where they cross the intercepts, the x and y intercepts. The top would be 0 at x equals 1/2. So x equals 1/2. Look, if you're marking this out like this, x equals 1/2 would be right there. So that would be your x-intercept. And then if you plug in 0 for x, you get -2, and that gives you your y-intercept. So this graph crosses the y-axis at -2. And that gives you roughly how that part of the graph looks. Oh, let me do it in blue. I didn't find any more points. But if you did find some more points, you would find that the rest of the graph looks like this up here, with never crossing the vertical asymptote. And in this case, just it gets closer and closer to that horizontal asymptote. And that's like a guide for it. Okay, but what is this definition saying? If we can use this graph to help us decide. It says, if the absolute value of y goes to infinity as x goes to a, then the line x equals a is a vertical asymptote. Well, if you start tracing your graph and looking at your y's, up here, this part of the graph, notice that the y values are shooting up to infinity. F of x is going to infinity there. And if you looked at the absolute value for this bottom part, as this bottom part approaches, in this case, x equals 2. In this case, our a is 2. Sorry, not x equals 2. It's, oh my gosh, x equals -1. So as it gets closer and closer to there, if you did the absolute value of this part, that would flip it up. And that would get closer and closer to that -1 as well. So x equals -1 is the vertical asymptote. Then, if you're looking at the pattern, of the function, as the absolute value of x goes to infinity, as your x going to infinity would be going to the right, what is f of x approaching? Well, f of x is approaching that horizontal asymptote there, that y equals 4. So that's another indication of what's happening there with that definition. Now, if you read your book, they go into like, how can you determine what's happening? Let's say you don't use a graph. Let's say you just use the function straight up. 4x minus 2 over x plus 1. Well, it's already in lowest terms, and we already know how to find the vertical asymptotes. But what we can do is we can take a look at this and see what the highest power of x is in the entire expressions there. Highest power of x and we've just got x to the first. If you had an x squared in there, you would use x squared. If you had an x cubed and it was the highest, you would use x cubed. But you're going to divide each term in the numerator and denominator by that x. So if you have 4x over x minus 2 over x all over x plus 1 over x, then you might see if you can do any simplifying. You'd end up with 4 minus 2 over x and then x plus 1 over x. Oop, I didn't put an x there, sorry. So that'd be 1 plus 1 over x. Excuse me. As x increases without bound, the quotients, the 2 over x and 1 over x, approach 0. If you think about how that graph looked when you were learning how to graph, like y equals 1 over x, like in that previous video, as your x increased without bound, the graph got closer and closer to the x-axis. So that 2 over x and 1 over x approached a value of 0 for y. So you're left with 4 over 1. So that line, y equals 4, is that horizontal asymptote. It's what your entire function is approaching as that absolute value of x increases without bound. So that's one way to look at it when you're trying to look at it analytically instead of graphically. Trying to decide like what is truly happening as far as limits are concerned. I'm not going to be too worried about you understanding all the limit information just yet. That'll be a little later. But it's something to keep in mind for the future for calculus. I'm sure most of you are heading to calculus. So that's something to keep in mind. But otherwise, for now, you can always just keep remembering your shortcuts. Looking at your degree of your numerator, degree of your denominator, and then deciding on your horizontal or oblique asymptotes from that. All right. Okay, so that's all I wanted to say about that. This was the addendum to the college algebra video because you guys are now in pre-calculus. I hope you have some good information there, and I look forward to talking to you again.